In this video, we're going to talk about how to determine electron configuration. Now, this is really important. This will become really important later on when we're talking about in molecules, because this will help us determine the reactivity of molecules and also define other properties of the molecule. And so in this, we're going to do a simple example of figuring out an atomic electron configuration, for instance, of an atom of carbon. Okay, and so with carbon, we know that we have 6 valence electrons. And as we've discussed in the videos prior to this, right, we can arrange atomic orbitals in a particular fashion where we have the lowest energy is the 1s orbital, and as we go up the board here, we have higher energy. Okay, so energy increases. All right. Whoops. So we have increasing energy as we go up the board. So the question is, how do we arrange those electrons within these orbitals? So the first thing we need to think about is what's called the Aufbau Principle. Okay, and what this says is that electrons go first fill the lowest energy orbitals. Okay, so if we have 6 electrons, we need to figure out the electron configuration, where they go. We're going to take that first electron and we're going to put it in the lowest energy orbital. So that is going to go in the 1s orbital. Okay. The next thing we need to think about is called Pauli exclusion principle. And so what this says is that each electron must have a unique set of quantum numbers. Okay, so if we're thinking about a 1s, what are our quantum numbers? Well, n is equal to 1, L is also equal, or L is equal to 0, and then ms, or ml rather, is also going to be equal to 0. For an s orbital, it can only equal 0. And so the only one that can differentiate between this and another electron is ms, which can have values of either plus or minus 1/2. Okay, so if we take this first electron that we put in here as positive 1/2, what that means is in order to have another set of unique quantum numbers, then we can put another electron within this orbital, but it has to have the opposite spin. And so every electron must have a unique set of quantum numbers. Okay. So this satisfies the Pauli exclusion principle by putting the second electron within the 1s orbital with a negative 1/2 spin instead of a positive 1/2 spin. Okay. So now we've taken care of 2 of the 6 valence electrons for carbon. So the next 2 are going to be really easy. The next orbital up, according to I should back up. So what that means is this 1s orbital is now filled. Okay, no more electrons can fit into that orbital. So we go to the next highest energy, right, or the lowest current unfilled energy, which is the 2s orbital. So as we did with the 1s orbital, we can also fit 2 electrons into here. Okay. And so now we've accounted for 4 of the 6 valence electrons. Okay, so again, now we return back to the Aufbau principle. So the electrons must fill the lowest remaining energy orbital. That's going to be the 2p orbital. Now, here it seems pretty simple. We could, for instance, but the problem is there's several arrangements of how we could put the electrons. So we could put the electrons here, like this, so have it fill one of the p orbitals, or we could fill like this, or we could fill the orbitals like this. So each of these would satisfy both the Aufbau principle and the Pauli exclusion principle. So in order to figure out which configuration is correct, we need Hund's rule, okay? And Hund's rule says electrons arrange electrons will be arranged to give, to maximize, we're going to phrase this, to maximize the spin. Okay? And so what that means is if this has a spin of positive 1/2, this electron, this has a spin of negative 1/2, right? What we have is a spin total equals 1/2, whoops, a spin total of 1/2 plus negative 1/2 equals 0. All right. Now, we could also, if we had this configuration, we would also result in the same spin. But in this configuration here, we would have spin total equals 1/2 plus 1/2 equals 1, and that would allow us to have the lowest energy configuration, electron configuration for carbon. And so what we end up with is, this is our most stable configuration as written like this, and this is from following the Aufbau principle, the Pauli exclusion principle, and Hund's rule.